Okay, so so how do you form the human body step by step? You already saw this in chapter 1. So we start at the atomic level. Atoms of the major elements, including carbon, hydrogen, oxygen, nitrogen, phosphorus, etc., they chemically react to form the macromolecules, like nucleic acids, proteins, lipids, and carbohydrates. And out of this, we make organelles. And these organelles are small parts of the cells that forms the unit of life, which is a cell. This unit, it has physical properties and physiological properties and anatomical properties that makes it to work as an independent unit. And we have a little bit over 100 different types of cells that they organize into those particular types, and then they form tissues. So we have the tissues then, that 2 or 3 tissues combine and then form organs. And the organs either physically connect, in the case of the most of the 11 organ systems that we have, or chemically connect, like in the case of the endocrine system, to form a functional organ system that all together form our organism. Now let's move into isotopes. What are isotopes? So isotopes are versions of these atoms that has different number of neutrons. So they all are atoms, all the isotopes, and they have the same number of protons, but they have different number of neutrons. An example would be for hydrogen. We have 3 types of hydrogen. We have hydrogen 1, we have hydrogen 2, or D, and hydrogen 3, or T. So this one, the hydrogen 1 is called proton because it has 1 proton and 0 neutrons. So this is the most common type of hydrogen that we have, but we have variations in which we have, for instance, in here one neutron and 1 proton, and this will be deuterium, or 2H. And then the one that has 2 neutrons and only 1 proton will be tritium, or 3H. So then, because atomic mass is based on accounting the weight of the protons and the neutrons that are found in the nucleus of the atoms, what you can expect as you increase the number of neutrons in some of these elements, you will expect to have heavier atomic mass when you increase the number of neutrons. And then in order to calculate the atomic mass, it's not like saying, well, how many protons and neutrons you have, and if you just remember the atomic mass unit, which is basically the unit that is used for calculating the mass of the atoms, well, a proton, it is a little bit less heavier than a neutron, but they have a little bit over 1 atomic mass unit. So it's like 1.008 or so for one of the 2. And then the other one, it's a little more heavy, like 1.009 or so, like the neutron. So in the case of hydrogen, if you look here, in this periodic table that we have in the wall, this number in the bottom of the abbreviated name for this hydrogen is 1.01. Why? Well, because this atomic mass is calculated based on the majority of the type of hydrogen that you have, which is basically proton. It's not specifically 1, is 1.01. So, I mean, if you see, with few exceptions, like in the case of chromium, you have most of the times a decimal after the big number there. So there is a variation then. And depending on which variant of the atom or the element it is more frequent, it is basically how the average is for the atomic mass. So just as an example, let's say that in this room we have a range of weight between, let's say, 100 pounds and 170 pounds. But the majority of the people is like around 120 pounds. So if we were to calculate our atomic mass, or basically our weight, what will be the number that you will expect? So would you expect more the average to go to 100 or to 170? Or will it go around 130? So most of the people will be within that weight, 130. And then some of them, maybe I said 120, I don't remember, but let's say 130. So most people, like let's say we are 20 in the room, let's say like 15, they weigh around 130. And then there are 2 or 3 that weigh 110 or 100 pounds, and then we have 2 that weigh 170. So where do you expect to have the range going? Into 100, 170, or 130? 130, because that's where we have the most. So similarly here, protein, since it's the most common form of oxygen, then you expect to have this atomic mass close to 1.01, rather than this one that will have an atomic mass of 2.0 something, because each of these weighs 1 atomic mass at least. And this one will be the heaviest, will weigh basically 3 times what this one weighs. Okay, so now, well, some of them can be stable, meaning that they don't emit energy. So like in the case of protein and deuterium, but some of them, they can be radioactive, like in the case of 3H. And then for carbon, we have here 2 isotopes. So we have carbon-12 and carbon-14. So carbon-12 is also known as 12C, this one 14C. And this one has 6 protons and 6 neutrons, while this one has 8 neutrons and 6 protons. So 6 plus 8, it is 14. That's why we call it carbon-14. So this is the most common type. So then what you expect to see in carbon, it is to have 12.01 as atomic mass. And then for this one, is radioactive. It emits energy, and it is actually used to date artifacts that are found in nature. So basically tell the age of these molecules that you find. So now, because they can emit energy, which we know as radiation, the nucleus is disintegrated until you reach stability in the nucleus. You can use them in medicine. So you can use them either to have some imaging studies, or you can use them actually to treat diseases. If you use it in medical imaging studies, like for instance positron emitted tomography, basically you can diagnose metastases or tumors. So you give glucose to the patient to drink with these radioisotopes, and then if A group of cells undergoing constant mitosis basically are dividing without a purpose. They can emit that energy. You take a scan of the body of the person, that specific area, and then you can see normal tissue that takes up less glucose than a tumor. And then you can see the emission of these positrons in these scans. That can see a red color in these films. So then it is a functional study, PET scans. And also you can use it for bone scans. And in some cases, you can use it to treat diseases like hyperthyroidism or even cancer in the thyroid gland. So thyroid gland uses iodide to form thyroid hormone. And in this case, we have a form of iodine that is called iodine 131. And when the person ingests this radiation is going to start destroying the nodules, if it's hyperthyroidism, or the tumor in the gland. Now, one thing when this is used to treat that is that the person has to be quarantined in a way until that radiation disappears. Because otherwise that radiation can affect people around this person. And you don't want someone to get around you. You can tell them, don't get next to me, I'm radioactive. Okay, now let's see what are mixtures and what are compounds. So mixtures are basically substances where you physically combine the molecules. And they're physically combined, but they don't change their properties. So they don't react chemically. An example of daily life, water and sand. Water and sand are physically combined and they form a mixture. So an example in our body is blood. So we have cells and a liquid, a solid, which are the cells, and a liquid, which is plasma. If you let this test tube where you take the blood sample to stay there in the tube rack, the cells, because they're heavy, they will fall out of the solution, they will go into the bottom of the test tube. And the liquid goes to the top because it's less heavy. So that's a mixture. Now we have chemical compounds in which you actually have changes in both molecules. So these can be substances formed by atoms of different elements that are chemically bonded, and they have unique properties different from their origin. So they cannot be separated by physical means. An example is water and carbon dioxide. So we have three types of mixtures. So we have a suspension in which the molecules are large. We have colloid in which the particles are small and are not visible, but in the case of suspension, the molecules are visible, so the suspensions are opaque. The colloid sometimes can be opaque, sometimes not, depending on the concentration of these small particles. If it's a lot, then it will be opaque. If it's not so much, it will be clear. And then solution, the particles are very small. And independently, whether it's highly concentrated or not as much concentrated, these solutions are clear for the most part. So examples of suspensions, blood as well. So it's a mixture. You have the red blood cells in plasma. In the case of colloid, we have the cytoplasm or milk. The proteins of milk are medium size or small size, and they will be suspended in water. In the case of glucose solution, well, glucose gets dissolved into water. So, what is the difference between a solvent and a solute? Well, a solvent typically is the substance that dissolves another one, and the solute, it is the solid particle for the most part, or it can be a liquid as well, in which you have the minority of the solute, and then it dissolves in the solvent, which is the greatest substance in there. So an example will be salt or glucose, will be these molecules that can dissolve into the solvent, which is water. So you can make saline solution or a glucose solution. And both of them are used to put an IV line. And they can vary the concentration. So here we have the examples of mixture types. So here we have a suspension, large molecules or particles, like in the case of the red blood cells, suspended in water molecules. And then again, by gravity, these erythrocytes settle into the bottom of the test tube. And then milk proteins, they will basically be suspended in this water, but they don't settle. And in solution, the molecules are also combined with water, in this case glucose, with water molecules, and they don't settle as well. Okay, now let's talk about the unit that we use to measure the concentration of solutes in a solvent. So this one is called molarity or molality. Sometimes it's called molality. The abbreviation is letter M, and it tells you the moles. That's a unit. The number of molecules that you have per liter of a solution. 1 mole is equivalent to 6.022 times 10 to the 23rd units, which can be atoms, molecules, or ions of a substance. This is also known as Avogadro's number. And the molarity is expressed as molarity per liter, or simply molarity. 0.5 molar, you can say, okay, half of a mole. And the unit, it is the same, 1 mole. And that unit will be, or the number within that unit will be 6.022 times 10 to the 23rd. So, molarity, it is used to measure substances like electrolytes, sodium, chloride, etc., glucose, and also gases dissolving body fluids. So why this matters? Well, because we have sensors in the hypothalamus that detects how many molecules you have of a particular substance in your blood. And that can trigger the thirst mechanism. These sensors or these receptors are called osmoreceptors. And the typical osmolarity or concentration of molecules that we have in our body is between 275 to 295 millimoles per kilogram. So basically it's 1,000 of this unit. If you have eaten like hot dogs, pizza, ice cream, or a sugary drink, later on you start like 10 to 15 minutes after you start feeling thirsty. Why is this? Well, because these are either rich in sodium, which increases osmolarity or the concentration of ions in your body, or increases the levels of sugar, glucose. So that makes you to feel thirsty. That pulls water from your cells, that dehydrates you. And that triggers that thirst mechanism so you can start drinking water. And again, everything is based on this unit, 6.022 times 10 to the 23rd, the Avogadro's number. So, I'm a millionaire. I have 1 million already. Do you believe that I'm teaching here with 1 million? Well, I didn't grab. But guess what? My money is monopoly money. But still, I'm a millionaire. That's the unit. It's 6.022 times 10 to the 23rd. Can have 1 million pesos. Still, I'm a millionaire, right? So that's the unit. How many pennies do you need to make $1 the unit? 100. So that's molar, okay? Okay, so now let's see how atoms can form chemical bonds with other atoms. So then we said that protons and neutrons are found in the nucleus of the atoms, while they are surrounded by electrons in the orbital shells. And then the first shell holds 2, the next one holds 8. And depending on the atom, it is how many will have in its first, second shell, etc. So something that happens is that atoms, they feel, well, they will basically combine with others to help to fill those outer shells. Like in the case of the second, we can hold up to 8 electrons. So then, depending on the number of electrons that this atom have, is whether it will donate electrons or it will accept electrons to complete the 8 electrons that the second shell is supposed to have into what we call the octet rule. So the outermost electron shell of an atom is called the valence shell, and this is what it will determine how this molecule is going to interact. So we have here in this column these inert gases, which they have already filled their shell with the number of electrons, where they cannot fill any more electrons in their shell. So there is no need for them to combine. They already have their set of 8 in their last shell. So these are called inert gases. So then if they have less or more, is whether they are very likely to combine or not. And the likelihood for an atom to combine is called electronegativity. The more electronegative that this atom has, it will be more likely to combine. So atoms then can gain, lose, or share electrons to fill their valence shells. So one way to form some molecules is by sharing electrons or by donating or accepting electrons. When molecules donate or accept electrons, atoms donate or accept electrons, they will form something that is called an ionic bond. And an example that happens in nature is the combination between sodium atoms with chlorine atoms. And they form a molecule, a salt, that we know as sodium chloride. Sodium is a metal, chlorine it's a non-metal. So metals tend to combine with non-metals. And then we can also have the sharing of electrons either unequally or equally. If you have equal sharing of electrons, you will have something that is called nonpolar covalent bond. Like in the case of oxygen, where they equally share electrons. So one atom of oxygen combined with other, and they share their electrons, they stay together. And now water, which is basically a compound in which you combine two hydrogen molecules with an oxygen, it is a polar covalent bond. Why? Because they are unequally share electrons. Electrons, in this case, spend more time with the oxygen than with the hydrogen when they share it, share the electrons. So this creates a partial charge. So the oxygen is going to be negatively charged, while the hydrogen is going to be positively charged. And what are the key differences? That when you have an ionic bond, you will have charged ions. The one that donates the electron becomes positively charged. The one that accepts the electron becomes negatively charged. Because when the atom donates the electron, is losing a negative charge, so it's going to become positive. And the one that accepts these electrons, since the electron has a negative charge, will increase its negative charges, so that will become negative. And then polarity basically is going to influence how the molecules form. So we have some proteins that has amino acids that are positively charged or negatively charged, or sometimes neutral amino acids, and then the proteins can fold or unfold based and get a three-dimensional shape based on the interaction between the molecules. Okay. So here is the cartoon showing you how ionic bonds form. So in this case, we have sodium and chlorine. So if you see in here, in the first shell, both of them, they have already filled their first shell with the 2 electrons. And this one, it has already its 8 electrons in the second one, so it has 2, 4, 6, 8. And it has the valence electron, which is this, with 2, 4, 6, 8. And then this one in here, it has 2, 4, 6, 8. However, before this, and this is when they combine. So you will have this sodium donating actually one of the electrons to chlorine, and this one will become negatively charged, while this one will become positively charged. So, because this one has 11 protons, it will have greater charges, positive charges than negative charges. So it's not going to be electrically neutral anymore. After this one donates its electron to chlorine, so that the chlorine will have 8 electrons in its outer shell. Okay. So after you have the transfer of these electrons, the one that donates the electron is going to be positively charged, and you would call it a cation. And the one that accepts the electron is going to become negatively charged and is going to be called an ion. And opposite charges attract, so that creates a strong bond between the ions when they are combined in nature as sodium chloride. So now for covalent bonds. So instead of, sometimes some of these molecules to donate or accept electrons, it will be making more sense for them to share the electrons. That way, both of them, they have their outer shell complete with 8 electrons each. So now, depending on how many electrons do they share, is how would you call this covalent bond. So if they share one pair of electrons, it's going to be a single bond. If they share 2 pairs of electrons, it's going to be a double bond. If they share 3 pairs of electrons, it's going to be a triple bond. And now, classification of these covalent bonds by electron sharing. Non-polar when you have equal sharing, and polar when the sharing is unequal. So here we have an example of a covalent bond. So you have 2 hydrogen molecules. Each of these has only 1 electron. And they get close together in proximity. So it makes sense then for these 2 molecules to complete their outer shell, the first only one that they have, by having 2 electrons in their outer shell. So in this case, you will have what is called the duet rule for the first shell. So before, when they were apart, they only had 1 electron, but then when they get together, they have 2 electrons. So basically that's the sharing. And they form what is called the molecular hydrogen. So what type of covalent bond is this? Single covalent bond. And then in terms of polarity, in terms of charge, is it polar or non-polar? Non-polar. Why? It's equal sharing. Basically, the electrons spend equal amount of time between both hydrogen bonds. And then here we have the previous bond. It's a non-polar covalent bond. And then here we have a polar covalent bond. So this is oxygen and this is hydrogen. So if you look at oxygen, it has this amount of basically electrons in here. So it has 1, 2 in its first shell, and then how many protons do you have? 8, right? So you're supposed to have 8 electrons, right? So you have 2 here, and then you have 6 in here regularly. So how many does the oxygen needs to complete the octet rule if it has 6 electrons here? 2. Where does it going to get them? From 2 hydrogens. And that's why it attracts 2 molecules of hydrogen. So it can get 1 electron from this one and an electron for this. And at the same time, it shares one of the 6 that it has with this and another one of the 6 that it has, and everyone is happy. Now, because this one has more protons, see, it has 8 protons versus 1, then the electrons will be more attracted to this positively charged oxygen than for spending more time with the negatively charged hydrogen, or less positively charged, I should say. So then that creates polarity. That's why it's called polar. So you will create a charge. So the oxygen is going to be negatively charged, while the hydrogen is going to be positively charged. So, couple has children. They stay, of course, together the 7 days of the week, and they stay with their children. That's equal sharing. That's non-polar. Couple splits. The children spend more time with mom or dad than with mom or dad. And then in that case, the one that they spend more time with, like the weekdays, that creates a charge, in this case negative. And then the one that they spend the time only during the weekends, that creates a positive charge for that person. That's non-polar, polar. So it can be equal or non-equal. Now for hydrogen bonds. So hydrogen basically hydrogen bonds form when you have a weak attraction between hydrogen atom in one molecule and an electronegative atom like oxygen and nitrogen. Basically, hydrogen can combine with many molecules. But when it encounters something that is electronegative, like oxygen, nitrogen tends to combine a lot, including carbon. So now, hydrogen bonds affects water because they make the water molecules to stay together. So it's not only intramolecular bonds that these hydrogen atoms form with oxygen, but also you have intermolecular forces, single molecules of water can combine with others through hydrogen. And this creates surface tension that allows for aqueous solutions to basically form like drops or droplets. And that basically helps to make the water to be resistant to rupture by having this surface tension. And also it helps to support small organisms. And then water itself is the most important fluid that we have in the human body, or solvent. So then here we have intramolecular bonds of hydrogen with oxygen, but hydrogen from one molecule of water can combine with another molecule of water by breaching, creating hydrogen bonds between oxygen that has a negative charge and this one that has a positive charge. So it's like networking. You can have strong bonds with your family, but if you're in a workplace or school, if you make friends, well, that basically creates a network. So in this case, we form these droplets by creating surface tension. So these are hardly ruptured when, of course, we have water at the right temperature. So then, as a summary of how chemical reactions happen, so that reactants, they need to be nearby as well. So there are motion within these molecules, and that motion or movement can make the molecules to collide. And then these molecules can be attracted by electrical charge. Positive get attracted by negative, negative get attracted by positive, but negative do not interact with negative, and positive it doesn't interact with positive. That's the law of the opposite attracts. Okay? But again, you have to have the reactant molecules nearby. If someone wants to date, it has to go out. Otherwise, how is going to know that person people? Right? And then in some chemical reactions, you have molecules that can speed up these chemical reactions. And these molecules are known as catalysts or enzymes. Chemical reactions still can take place, but these enzymes reduces the speed of the reaction. Yes, you go out trying to date, but what about if you have a friend who's very sociable and knows more people than you, and you're a shy person, you're always there in the corner, don't speak to anyone, and then your friend brings the potential date for you. That's the enzyme. That speed up the chemical reaction. That's Cupid there for you guys. So then enzymes basically join the molecules by creating a chemical bond. And then these enzymes do not deplete, and it doesn't change by the chemical reaction. So you don't lose your friendship, no matter that you dated that person, didn't turn out to be not the right person for you. So that's the enzyme, do not deplete, okay? And then products of the chemical reaction and energy are released. So as we have a chemical reaction, we not only form bonds, or maybe you break bonds, but also you release energy that basically is in the form of heat, and that heat is actually important for the chemical reaction to happen, because we require a certain temperature for the molecules to be in motion. And then enzymes reduces the amount of activation energy needed to start the reaction. And again, is what I said before, you can still have a chemical reaction, but this will happen slowly, as if you don't have the enzyme. And what do you need for a chemical reaction to happen? Well, you need to have the reactants, the molecules that are going to interact, but you have to have it at the right concentration. You have to have a specific temperature and a specific pH or concentration of hydrogen ions, and a specific amount of enzyme, and the right enzyme. Okay, so that was the segment about chemical reactions. Now let's talk about forms of energy. So with that, we have different forms of energy, and energy basically it is defined as something that is needed for a chemical reaction, I guess, to happen. So we have different forms of energy. We have potential energy and kinetic energy. Potential energy is a stored form of energy. It's like when you're charging your battery in your phones or your electronic device. You're storing energy into that battery. That's potential. That can be transformed into kinetic. Kinetic is energy in motion, basically. And then both of them are interconvertible. So the kinetic energy can be converted into potential, and potential can be converted into kinetic. So in the human body, we have electrical energy, which is basically action potentials that transfer across these plasma membrane in excitable cells like muscle cells, nerve cells. Then we have chemical energy, which is basically storing bonds or releasing reactions like when you break ATP, adenosine triphosphate. And then mechanical energy is the movement of muscles and joints. And then chemical reactions in the body requires energy or input. So basically, in order to generate energy, you have to start also moving. So here we have cartoon showing you energy types or illustration in action of the enzymes. So A chemical reaction can be seen as someone pushing a ball to the top of the hill. So in order for you to bring that ball into the top of the hill, you have to spend energy. So you have to have kinetic energy. And then once this ball reaches the hill, you let it go. This will continue going down the hill on its own, and that basically is still kinetic energy. Now, you have a specific amount of energy of the reactants, as you see here in this graph. Energy is found in the y-axis, and progression in time is in the x-axis. So this person, in order to push the ball to the hill, it has to have or has to spend the potential energy that the person had to reach that transition state, which is when you have the ball on top of the hill. So that difference between this starting point and which will be this, and when you reach the top of the hill is going to be called activation energy. Now this activation energy can get reduced when you have an enzyme. So basically it's like bringing down the hill so that you don't spend as much of this potential energy that you have, and then you will have the reaction to take in a shorter amount of time. So basically enzymes, what they do, they reduce the activation energy for the reaction to take place. Now let's look at what is a chemical notation. So chemical notation is basically writing down your chemical reaction either in a piece of paper or an electronic form. And when you write a chemical reaction, you have to put reactants to the left, products to the right, and an arrow that tells you what is the direction of the chemical reaction. Sometimes it can be bidirectional. It can go in both ways, toward the products, or the products can be converted into reactants. And then when you have two different reactants that you will combine, you put a plus sign in between. And when the reactants are already together, you don't have this plus sign. But when you have two different products, then you put a plus sign on the right side of the chemical reaction. So now, in chemical reactions, the atoms can form bonds, they can break the bonds, or they can rearrange their bonds. And in this case, we have, for example, a synthesis reaction or anabolic reaction, in which two different reactants, A and B, will be converted into a product that or A plus B will be converted into a product that we call AB. So this is also known as condensation reactions. So you form a bond between A and B. And then you can have the opposite. You have the composition reaction or catabolic reaction, in which two reactants were already chemically bonded, and you break the bond between A and B, and you end up with two products, A plus B. And then you can exchange or transfer. So you can have A and B plus C and D, and you can have different products. You can have AC plus BD because you basically combine these two with these two, or you can have combination of A and D, like here, and B and C, like this. Proportions, well, it depends on the number of reactants and the type of the reactants. But this is a transfer or exchange. And then reversible reaction, like you can have A and B plus C and D converted into A and C plus B and D. And this AC plus BD can be converted into AB and CD. So we will see, for instance, one way to control the amount of hydrogen ions that we have in our body is through having some exchange reactions with an enzyme that we call carbonic anhydrase. And that it's basically a system that we will see over and over again of reactions or some chemical reactions that we have in the body with this enzyme that basically help us to have either more hydrogen ions or less hydrogen ions, and this is what we call a buffer, because it can absorb or can release hydrogen ions depending on the needs. So here we have an example of enzymes participating in an anabolic reaction. So let's see, it starts in here. So basically you have two substrates. This one in orange color, this one in yellow color, or red and orange. So enzymes have gaps in them that are known as active sites, and these active sites, they correspond to the three-dimensional shape of this enzyme. So they fit. This is what is called the key lock mechanism. So this substrate specifically fits into here, this one into here, and even between the substrate, you have complementary shape. So the enzyme, once it binds these two substrates, embrace them and brings them together. And they have basically a chemical reaction happen that after the transition state, you will release the products that now are different from the initial substrates. Any questions? Now in our body we have many enzymes. Some of them they are critical for life, others not so critical but they are important, including lactase enzyme. Lactase enzyme, it's an enzyme that helps to break down the glucose, the molecules that are found in milk, like glucose and galactose. Glucose and galactose are monomers of carbohydrates. And this enzyme then is necessary to break it down so that we can absorb this glucose and lactose or galactose, and then we can have nutrition. Well, some people might be deficient in this enzyme, and they end up with what we call lactose intolerance. And lactose intolerance sometimes it can happen early in life, but it can happen later in life. This it's one example. Another example is the deficiency of this enzyme, hexoaminidase. So this enzyme is necessary for the normal functioning of the neurons, the cells of our brain. So when someone has this deficiency, it can have this disease that is called Tay-Sachs. And then we have enzymes like, for instance, adenosine deaminase that helps for our immune system to be strong. So we can have a disease in which we will have deficiency of this enzyme, and then we will have what is called severe combined immunodeficiency, and the person will be having a lot of infections. Their immune system is not as strong. And an enzyme that also can be defective or absent is phenylalanine hydroxylase. So phenylalanine hydroxylase helps to convert tyrosine into phenylalanine. And then when this enzyme is deficient, we accumulate byproducts of this amino acid metabolism, and then these byproducts will be toxic for our brain, and they basically can produce mental retardation. So there are some tests that can be done to see if a baby born with this disease, phenylketonuria, and then if the baby has this deficiency of this enzyme. For the first years of the life of the person, you will avoid foods that are rich in phenylalanine. And then later on in life, some of them, they can develop tolerance to these products. Any questions? Okay, now let's look at what are inorganic compounds and how they are important for our body. So inorganic compounds are the opposite of organic compounds. So they don't contain carbon and hydrogen bond. Organic chemistry basically studies carbon and hydrogen bonded molecules. And then we have several inorganic compounds in our body, those ones that they don't have bonded carbon and hydrogen. So the most important inorganic compound that we have in the body is water. See, it doesn't have carbon and hydrogen. It has 2 molecules of hydrogen and 1 of oxygen. And it can make up to 60% of the human body mass. In males, their body is composed per weight, 60% of the body weight in males is water, in females is 50%. So if someone weighs 100 pounds, it's a female, the number of pounds of water is going to be 50 pounds, because that's 50%. And then we have acids, different kinds, including hydrochloric acid, molecules like hydrogen, and carbonic acid, H2CO3. So acids are molecules that donate hydrogen ions. And then we have bases, molecules that accept hydrogen ions, like bicarbonate, HCO3 minus. So here we have this diagram showing you, like, for instance, if you have here in this beaker water molecules that tend to dissociate into hydrogen molecules and hydroxyl. Hydroxyl molecules is basically OH. So they tend to dissociate equally in neutral water. So if you add an acid like hydrochloric acid, this will increase the concentration of hydrogen molecules. So that water becomes acidic. Now, if you add a base like sodium bicarbonate, that's a base. So in this case, this base is going to absorb hydrogen, and this solution is going to become basic. So it's going to have less hydrogen. Any solution that is acidic has more hydrogen than hydroxyl groups. And any solution that is basic, it has less hydrogen. So those are acid and bases. Now let's talk about the properties of water. So water can absorb heat, and it can carry the heat to help to dissipate higher body temperature, for instance. And water can carry the heat when it changes from liquid to gas. So when it evaporates, it can carry the heat. Water is forming part of several fluids in our body that cushions our body, like pericardial fluid, pleural fluid, peritoneal fluid. Also, it lubricates to reduce friction, like we have a watery solution in between the joints that is called synovial fluid. It lubricates our joints. And water is a solvent. Basically, it can combine with sodium chloride. It can combine with glucose and other ions or molecules. And then because it is polar, it can subdivide major groups of chemicals into, or compounds, into hydrophilic or hydrophobic. Basically molecules that like water, hydrophilic, or molecules that they don't like water, hydrophobic. So pure water has a pH of 7. pH is the concentration of hydrogen ions. So in this case, hydroxyl groups or OH minus will be equal to hydrogen ions. So this is basically what it happens with water. Water can dissociate into hydroxyl groups and hydrogen, or these two hydroxyl groups and hydrogen can form water. Any questions? So how these electrolytes or charged molecules form in water? Well, if you add salt into water, because water molecules, they have a negative and a positive charge, these positive or negative charges can attract different ions from that salt. In this case, the sodium chloride will be spread, and you will have, they will break their bonds, and then you will have sodium, which has a positive charge, attracted by oxygen, which has negative charges. So you will basically form a coat of oxygen around sodium. And then chlorine atoms that now are going to be called chloride after they gain their negative charge, they are going to be surrounded by the positively charged hydrogen. And then you will form spheres. So you will hydrate this chlorine, or now it's going to be called chloride, and then this sodium atom now is going to be called a sodium ion. So this is an ionic compound, and ionic compounds are hydrophilic. And then in the case of polar covalent compounds, they are also hydrophilic. In this case, we have carbon monoxide, which is basically having one carbon attached to one oxygen. So this one, this carbon, which has a positive charge, is going to be basically interacting with water and the oxygen with these negative charges attracted to this carbon, and the oxygen of carbon dioxide, which has, monoxide that has negative charges, is going to interact attracting these positive charges from hydrogen. So see then how these water molecules can move around so that you can basically interact with the different molecules. So these are hydrophilic compounds, both CO, which is carbon monoxide, and sodium chloride. Now, a nonpolar hydrophobic compound. So nonpolar basically will be a molecule that it doesn't have a charge. Hydrophobic, well, if it doesn't have a charge, it's not going to interact with the charges of water. That's why it's hydrophobic. So in this case, we have methane gas. Methane gas is made by one molecule of carbon and how many of hydrogen? 4. So see how this carbon is surrounded by 4 hydrogens? So if you put in a closed container that has water, if you put methane gas is not going to dissolve in here. So why? Because this one doesn't have a charge, so it's nonpolar, and this one has charges. So this molecule is basically having no interaction with water, that makes it a hydrophobic molecule. So now let's look at what is pH. So pH, it is basically the concentration of hydrogen ions. It's a measure of that concentration. And this pH is measured in a scale that ranges from 0 to 14. 0 is extremely acidic, 14 is extremely basic. In the left side of this column, you have how many hydrogen ions you have. In the right side, you have the column with the number of bases. In the case of the hydrogen ions, the more acidic that the solution it is, the more hydrogen ions that you have, like stomach acid, vinegar, lemon juice, coffee, tomato, etc. And then in the case of where you have more base, like hydroxyl groups, you will have more in the case of the higher the number, like 13, 14, like in the case of bleach, ammonia, like that spray that you use to clean the ovens. It's a highly basic molecule. And then acidic pH will be when something is below 7, basic when something is above 7. So anything that is 7 is neutral because you have equal numbers of hydrogen and equal number of bases. Now, our blood has a pH that is slightly basic, between 7.35, somewhere around here, and 7.45. The range is narrow, and it has to keep that way because our cells are very sensitive to that concentration of hydrogen ions. And we have enzyme activity and metabolic reactions that help us to keep within that range. Any imbalance can lead to acidosis or having a low pH, so going in this direction, or going into a higher pH, which is known as alkalosis. And both of them disrupt health or homeostasis. So we will leave it up to there. Any questions?